Hello and welcome to everybody for joining my presentation about global market trends in optical coatings for consumer electronics, automotive and e-mobility applications. My name is Steffen Runkel. I am the Director and Global Head of the Business Unit Optics at Bühler Optics in Alzenau, Germany. Optical technologies are penetrating more and more in our everyday lives, and optical coatings are a key enabler driving many innovations. In the next 30 minutes, I would like to present to you selected applications and examples to demonstrate the importance of optical thin films and related challenges. Before I start with the core topics of this presentation, I would like to briefly introduce Bühler and Optics as a company. Bühler is a family-owned Swiss-based company. We are a machine manufacturer and solution provider for technologies used in the food, feed and advanced materials industries. One nice example of an application related to optical coatings is the electrochromic window facade of our Innovation Center Cubic in our headquarters, as you can see on the bottom picture. Bühler is not known to the end customer directly, but every day all of us are in contact with products manufactured on Bühler production equipment. From these pictures, you can already learn how often we are in touch with optical technologies throughout the day, and I will show you on the following slides what is hidden and how very thin layers can make a big difference in the performance of these products and how to produce them in a cost-efficient manner. Optics is one out of 12 business areas in the Bühler Group, belonging to the Advanced Materials division. Bühler Optics is specialized in the manufacturing of thin film vacuum coating equipment and corresponding coating processes with a focus on optical layers. Our headquarters is in Alzenau, Germany, close to Frankfurt, which is our main hub for R&D and manufacturing. Besides Alzenau, we have a second manufacturing site in Beijing, where we develop, design, assemble and commission coating machines for the local market in Asia, and produce selected standardized machines for the global market. In addition, we have a presence in Raleigh and the US East Coast with the focus on sales and service, as well as refurbishing used equipment and converting old machines into almost new machines. This is a sustainable solution by giving old machines a second life instead of throwing them away. Our product portfolio covers the full range of the optical spectrum, from extreme UV light, used for example for mirrors in EUV lithography, the visible range up to the far infrared range applied in night vision applications. As core coating technologies, we have magnetron and ion beam sputtering, ion and plasma assisted evaporation technologies, as well as PECVD used for diamond-like carbon layers in our portfolio. We offer coating solutions applied in 7 market segments. Traditionally, the precision optics market is our largest segment, building the base for new applications in new markets using optical coating technologies, like the automotive industry, semiconductor and consumer electronics segment. In addition, we supply solutions for the ophthalmic market by means of anti-scratch and anti-reflective coatings, as well as easy-to-clean surfaces on organic eyeglass lenses. And finally, architectural glass and automotive glazing, as well as coatings on flexible films in roll-to-roll applications complete our range of markets. Today, I would like to show to you selected examples on how optical technologies enable new applications in mobile electronic devices, today's and future cars, as well as energy-efficient solution for electrocars. So please follow me on the journey from classical applications in optics, like coatings of lenses and mirrors used in cameras, microscopes, lasers, lithography and night vision, to new photonics application used in smartphones, optical communication and many more. As a first topic, I would like to start with the usage of optical technologies in mobile consumer electronic devices. I believe most of you still remember the first cell phones in the late 90s. They were designed for one single purpose: to talk to somebody on the phone when you are on the road. A couple of years later, the first smartphones were introduced. These phones had colorful displays, cameras to take pictures with, and touchscreens to make them easy to use. Suddenly, easy to clean and anti-fingerprint coatings were required to keep the display clean. The resolution of the cameras improved step by step, requiring anti-reflective coatings, UV IR cut filters, and scratch-resistant coatings to protect the outer windows. First optical sensors were implemented to detect the ambient light, or proximity sensors to distinguish if the user is looking at the display or the phone is near your ears, that the phone automatically turns off the backlight and locks the touchscreen. Nowadays, our smartphones in the latest generation have optical face recognition sensors to unlock the device. And more functions will be integrated in the future, like extended reality applications, spectral sensing, and hyperspectral imaging to analyze, for example, our food, to provide us with useful information like sugar levels. Smartwatches measure vital functions of the human body, and smart glasses will be available with an integrated visualization to provide customized information. The next generation of smart glasses is slim and stylish and will no longer be ugly and uncomfortable. This means optical projection and sensors will become tinier for seamless integration. Such optical sensors require a variety of different optical filters, like color filters, luminous efficiency filters, or bandpass filters. Camera lenses are coated with AR coatings. The outer windows needs to be scratch resistant, and inner lenses with strong curvatures requires technologies like the Moose Eye process, combining structuring and coating to achieve broadest AR performance even under high angle of incidence. Other examples for coatings are fashion-driven colorations of the backside, as well as a protection of the surface with an easy-to-clean coating providing anti-fingerprint characteristics. As the variety of coatings and specifications is so broad, different coating technologies like magnetron sputtering in different arrangement and evaporation are required. Considering the production volume on an annual base, about 2 billion smart devices are sold worldwide. The challenge for the coating system is to apply simple as well as high-end and complex layer stacks in high volume at best yield. Now let's take a closer look at one of these sensors and the coating technique behind it. The 3D scanning sensors are used in a wide range of applications. On the previous slides, I mentioned face recognition for user identification, gesture control, and driver monitoring as safety functions. Another application on the way to autonomous driving is scanning the environment of the car by LiDAR sensors. Applications in the healthcare and medical sector, as well as industrial applications. LiDAR can also enable drones to fly autonomously and in combination with hyperspectral imaging sensors to define the agricultural technology of the future. By scanning the field, this information can be used for controlled watering and fertilization. This will help to save water and ease the impact on soil and groundwater. What kind of coating is required for such a 3D sensor? In a simple sketch, such a sensor consists of an infrared projector. The generated light is reflected by a person or an object and detected by an infrared imaging sensor. In order to have a good signal-to-noise ratio and a large field of view, the light hitting the detector must block all the disturbing light from the sun and the environment and let only the wavelengths of the near-infrared laser pass. For example, at 940 nanometers, which is considered safe and invisible for the human eye, such a bandpass filter can either be applied on a glass substrate mounted in front of the sensor, or directly on the CMOS wafer. On the next slide, you can see one example for a bandpass filter with low angle shift. The central wavelength is around 940 nanometers. Such a layer stack can be achieved by using hydrogenated amorphous silicon as high index and silicon dioxide as low index material. One coating technology to produce such or similar filters is a PALMS and PALMS Plus process used in the Helios coating system. It allows to apply complex layer stacks with up to 1000 layers, including thin layers, at highest precision, uniformity, and reproducibility. So automated handling system for wafers enable high volume production at highest yields. This coating tool can easily integrate it into an optics fab or semiconductor fab to combine multiple thin film layer coatings and lithography, allowing the generation of patterned optical filters on active device wafers. The coating process of the Helios tool is named Plasma Assisted Reactive Magnetron Sputtering, PAMS. Basically, a turntable carrying the wafers is in permanent rotation. At one position, a very thin metal or metal suboxide layer is applied by magnetron sputtering. This ultra-thin layer is not fully oxidized, therefore the achieved sputtering rates are high. By using a plasma source in a second position, generating active oxygen, the ultra-thin layer gets fully oxidized while passing this station. With each turn of the table, a few atoms thin layer is added. This allows us to create thick and even thinnest layer with excellent physical properties, as you can see in the small picture at the bottom center, showing the full amorphous structure and smooth interfaces of a layer stack in an SEM picture. The benefit of the PALMS process is the high stability of the process itself. In combination with an integrated optical monitoring system, we achieve highest reproducibility at high throughput for maximum productivity. The Helios tool is available in 3 different sizes to cover the needs of 8-inch and 12-inch fabs. The tool itself can be equipped with different process stations and configurations like automated wafer handling. Another application I would like to mention here is hyperspectral imaging. This is basically a combination of spectroscopy and imaging, enabling new ways of analyzing objects. I already mentioned agriculture and the analytics of food. In our company Bühler, we use this technology in 2 other business areas. One is food safety. Optical sorters can detect good products from foreign material of the same size and color, or even identify hazardous products, for example nuts, contaminated with alpha toxin, and separate them from the batch of wanted products. Another application is related to our area grinding and dispersions. Paints and colors produced on our machines are used, for instance, for banknotes. Hyperspectral imaging can be applied to identify the origin and confirm authenticity. Not only the color is identified, but also of what the color is made of. Final example of optics in consumer devices are smart glasses and extended reality solutions. Such devices are known to us in computer gaming or professional use, like for remote service support. This technology is of high value for our customers and reduces downtime of machines to minimum, being sustainable at the same time as reducing traveling of service technicians around the world. To become a volume market and to make such a product attractive for the end users, the projection optics and involved sensors and cameras need to become tinier in order to fit in an almost regular frame. Thin film coatings ensure and enhance the required performance of the optical components involved. From consumer electronics application, I would like to continue with the next part of my presentation, optical coatings in cars. The automotive industry is facing huge changes from the traditional car and manual driving, combustion engines towards more and more assisted driving on the way to fully automated driving and alternative green power engines. Two key enabling technologies for partial and fully automated drivings are once again optical sensors in combination with artificial intelligence. AI algorithms are required to analyze the collected data from the sensors in real time and to draw the right conclusions. Taking a look at the traditional car, for many decades now, optical coatings are used to apply reflective layers for the internal and external mirrors and the head and rear lights. In today's premium cars, new features are available based on optical technologies. Multiple cameras support the driver for easy parking or recognize road signs and keep the car in the lane. Night vision devices make things visible in the dark and in advance of the driver recognizing them. LiDAR and radar systems scan the environment and enable keeping a safe distance to the vehicle in front or trigger emergency braking in critical situations. As you can see, the safety of driving has improved a lot and some of these cars can already drive partially automated. And what is available in the premium segment today will soon become standard in the mid-range segment. This will change the requirements towards production by increasing the volume for such components easily by a factor of 10. That means batch production systems can fulfill the low volume requirements and fully automated inline coating systems are needed for cost-efficient high-volume production. In the future car, even more optical technologies will be implemented on the way to full autonomous driving and alternative powertrains. While today the car is designed so that the driver can observe the environment well, the driver needs to see. In the future, the car itself will be able to see. This will be done by fusing LiDAR and radar sensors as well as cameras covering all possible driver situations and distance ranges. The control of the car and its functions will work through gesture and the driver will be monitored in case an intervention is necessary. As a new feature, the car needs to communicate with its environment and other road users. One method is a projection of information via the headlights. For more than 100 years, the lighting of cars was powered by light bulbs. In the beginning, a full metal reflector was used. Later, a plastic body coated with a protected metal mirror. In the past decades, the lights became more powerful and smarter. Matrix light, laser light, and other technologies can control which part of the street and its surroundings gets well illuminated, and at the same time, drivers from oncoming vehicles will not be blinded. We see a clear change in the technology, from reflecting mirrors to transmitting and active elements. To maximize the light transmission, these optical components require an anti-reflective coating either by applying a thin film layer stack or a mousse-eye structured surface. In the future, even more intelligence will become part of the lighting. An integrated projector will enable the car to communicate with pedestrians by projecting symbols or moving elements on the street. It can also indicate in which mode the car is driving, manual or autonomous. One example of active light control is shown on this picture. Areas of interest are in the main light beam, while the driver in the oncoming car is protected from dazzling by active shading. Also, an excellent example is a YouTube video from Mercedes, demonstrating how a car can communicate with road users by active projection of information using light. New features like welcome function for the driver, to prevent collision at intersections with poor visibility, to communicate with pedestrians. I see you, you can cross the street please, as well as putting the human being in the spot again. In all these examples, a combination of optical sensors and projecting light techniques are key enablers. The biggest challenge is that the projector source are powerful enough that all this works not only at night but also at daytime. One of the famous sensors seen as key for autonomous driving is LiDAR, light detection and ranging. It is basically an optical scanner which scans the environment of the car. While the first LiDAR systems were quite large and driven by mechanical parts, today's and future LiDARs will be based on semiconductor solutions to be smaller and more cost efficient. Bandpass filters as well as scratch resistant transparent coatings on top of the front window are required. Inside the car, head-up displays apply augmented reality functions in the windscreen. In the field of view of the driver, information like speed and navigation symbols are shown for a more comfortable and safe driving experience. The eyes of the driver can stay on the road, especially in busy situations. Two mirrors are part of the projecting light path. One mirror is an enhanced aluminum reflector and the second one is a cold light mirror, separating the projected light coming from the light source from the disturbing sunlight, which under certain circumstances takes the light path in the opposite direction, will be amplified and could destroy the light source or even put it on fire, which happened to the first head-up systems. Depending on the production volume, either batch, evaporation or inline sputter coating technologies can be used for an efficient production flow. Let's stay inside of the car. Vacuum coating technologies are a clean and sustainable solution for metallizing 3D plastic components and trim parts used in the interior. In comparison to a classical electroplating, vacuum coating processes drastically reduce the water and energy consumption as well as fully eliminate harmful chemicals. Again, batch as well as inline coating solutions are available to meet the customer requirements on volume and to coat the parts as cost efficient as possible. The final part of my presentation will be focusing on automotive glazing, specifically in the context of e-mobility. On the previous slides, we already learned that the trends in the automotive industry are towards electrification and autonomous driving. Energy efficiency and comfort as well as safety for the passengers are important factors. The future automotive glazing needs to fulfill multiple purposes. The glass substrates are getting thinner and thinner to reduce the weight. Solar control and low emission glasses reduce the car of heating up and overheating in the sunlight and saves energy for air conditioning. Finally, electrochromic coatings can be used to fully shade the interior space or generate a private atmosphere. This also allows more freedom to designers. On the left picture, you can see the working principle of combined LowE and solar control coating. While the visible part of the spectrum is mainly transmitted, the UV part is fully reflected or absorbed, and main parts of the infrared spectrum are reflected as well. This reduces the heat load inside the car and reduces the energy consumption of the climate system. Such coatings can be achieved by a layer stack of protected silver. To increase the comfort and safety, a transparent conductive layer can be embedded in the layer stack. By applying electrical voltage and current and using the resistance of this layer, the windshield will heat up and improve the glare by removing fog or ice from the screen. The same technology is used for the protection window of optical sensors and camera systems in the car to keep them functional, especially in winter times. LowE, sun control as well as electrochromic and TCO layers for automotive glazing or architectural glass are applied in large area coating systems by using magnetron sputtering technology. These multi-chamber systems can coat large areas highly efficient in a short time. Smart control and closed-loop processing ensure autonomous operation, highest uptime and a high yield output. I am now close to the end of my presentation and I would like to summarize. In short, optical and photonics technologies continue to take up more parts of our daily lives, adding new features to products, improving comfort and safety. This success story will go on. In this presentation, I have shown examples that prove that more and more optical sensors and projectors will be integrated in mobile devices to offer new functionality now and in the near future. Scanning the environment and analyzing objects, using biometrical information to identify users of devices, to analyze the human skin or blood or monitor human vital function will become normal. Most of these coatings are done in mass manufacturing in Asia, mainly in China. New challenging filters are developed in the US and Europe, and in order to make sensors smaller are directly applied on structured CMOS wafers in semiconductor fabs around the world. The optical industry and the required thin film coatings will also support the automotive industry to increase the safety of the car and enable partial and full autonomous driving in the future. While established tier suppliers produce the classical mirrors, headlights, head-up displays, etc., which will become volume products while entering the mid-range car segment soon, new optical solutions like LiDAR, monitoring sensors, light projection systems are also an opportunity for companies in the category optical specialists or startups, or of course could be new business for established tier suppliers. All in all, we see the automotive supply chain is changing due to a paradigm shift in the technology and global challenges we face, including supply shortages. The reliability of supply chains became more important than ever before. This offers new opportunities, and electrical powered cars need smart solutions to increase the range of the car and improve the reliability, safety and comfort through sustainable energy efficient solutions. Thank you very much for staying with me during my presentation. I would happily get in contact with you in order to answer all your questions or to discuss your personal challenges in optical coatings. Goodbye, and as we say in German, tschüss und bis bald. Thank you.